Today we are going to see current of electricity. This is the syllabus for current of electricity. This is for physics code 9702. It's unit 19. This portion is only for AS syllabus. As you can see, the learning outcome, we have three subtopics. One is electric current. The second one is potential difference and power. The third one, resistance and resistivity. Under each topic, you have subtopics. But today in this video, we are going to learn only about the first topic, electric current. So under electric current, the learning outcome, you will be able to understand that electric current is a flow of charge carriers. Understand that the charge on charge carriers is quantized. Define the coulomb. Recall and use this formula Q is equal to IT. Charge is equal to product into time. Derive and use for a current carrying conductor the expression I is equal to Anvq, where N is the number density of charge carriers. However, in this video, we are not going to look in depth about this part B. Understand that the charge on charge carriers is quantized. I'll make a separate video and we will talk about it in that video. I'll leave a link below. Recall. All matter is made up of tiny particles called atoms, each consisting of positively charged nucleus with negatively charged electrons moving around it. This is a description of atoms. As we know, atoms consist of nucleus at the center, which consist of positively charged protons as well as neutrons. Around the nucleus, electrons are moving. Charge is measured in units called coulomb. The symbol is capital C. We all know charge is a quantity and it is measured with a unit coulomb. Atoms in metals have one or more electrons which are not held tightly to the nucleus. These free electrons wander at random throughout the metal. So metals have free electrons which is capable of moving around. When the battery is connected at the ends of the metal, the free electrons drift towards the positive terminal of the battery, producing electric current. As you can see, the central part, this is atom of the conductor, and these ends of the conductor is connected to the battery, positive terminal and the negative terminal. The free electron will move towards the positive terminal of the battery. Then the next atom's electron will go to the positive wherever the atom which lacks in electron. As a result, the movement will be towards the positive terminal of the battery. Hence, electric current is produced. The size of the electric current is given by the rate of flow of charge. This is the formula for current. As we know, current is the ratio of charge over time. In other words, the definition of electric current is the rate of flow of charge, the number of charge passing per unit time. Electric current is an SI-based unit. SI-based unit means it's a fundamental quantity, which means it does not depend on any other quantity. It can be simply measured directly. The SI unit of current is ampere. The symbol is capital A. So we have this equation, current is equal to charge into time. From this, we can make charge as the subject. We'll get charge is equal to current into time. Or we can write it in symbol, Q is equal to IT, where the charge Q is in coulomb, which is the SI unit of charge, when the current I is an amperes and the time T is in second. This gives the definition of the coulomb as follows. The coulomb is that charge passing a point in a circuit when there is a current of 1 ampere for 1 second. So this is the definition of the unit coulomb. So if I have to define coulomb, I have to say 1 coulomb means it requires 1 ampere of current passing for a time of 1 second. In 1752, prior to electricity being identified with the electron, Ben Franklin chose a conventional regarding the direction of current flow. Franklin assumed that positive charge carriers flowed from positive to negative terminals. So before they identified that the current is a flow of electron, Ben Franklin, he identified that positive charge is flowing from the positive terminal to the negative terminal, which is not correct. We now know this is incorrect. In metal, the charge carrier is the electron whose charge is negative. As we all know, electrons will be the only one carrier that flows. So we know that negative charge, which is the electron, is the only charge carrier. Hence, electric current is the flow of electrons in a circuit. So this is a contradiction to what Ben Franklin had stated. He stated that current is a flow of positive charge from positive terminal to the negative terminal. But that is not correct. We now know the electric current is a flow of electron from the negative terminal towards the positive terminal. Conventional current, on the other hand, is the flow of positive charge and is directed from positive terminal to the negative terminal of the battery. Since he had already stated, they are not changing it. Instead, they have mentioned it as conventional current direction. So the actual current direction is from the negative terminal to the positive terminal because electron is flowing. But the conventional current, we take it as positive charge is flowing from the positive terminal to the negative terminal. Remember that the direction of electrons is in the opposite direction of the conventional current. So as you can see in this diagram, when electrons move this way, the empty space, that means a positive ion, is moving towards this way. So that's why they are opposite to each other. So as you can see, from positive terminal of the battery to the negative terminal of the battery, we write it as current flow because at present we consider the conventional current direction. So that is from the positive terminal to the negative terminal. But in reality, the current is an electron flow, which is from the negative to the positive terminal. Conduction in a current carrying conductor. Drift velocity. Now there is a term called drift velocity. Drift velocity is the average velocity attained by charged particle in a material due to an electric field. So remember, drift velocity is the average velocity of the charged particle in a conductor. Okay, so we can see from positive to negative terminal, positive charge is flowing. This shows our conventional current direction, whereas we can see equal number of electrons flowing from the negative terminal to the positive terminal. This is the electron flow direction. This is a part of the conductor. The length of the part of the conductor I have considered is L. The figure shows part of the conductor of cross-sectional area A through which there is a current I. So the cross-section area of this conductor is A. Current I is passing through the conductor. The current in the conductor is from left to right, but the charge carrier is in the opposite direction by the drift velocity v. I'm considering the velocity, the average velocity of the charged particle as v, which is also known as drift velocity. Let n be the number density of the charge carriers. What is n? N is number density of the charge carriers. In other words, the number of charge per unit volume. In other words, for 1 meter cube, what is the number of charge passing through? Q is the charge on each of the charge carrier. L be the length of the part of the conductor considered. So I have summarized it. A stands for the cross-sectional area, I stands for the current, V is drift velocity, N number density of the charge carriers. In other words, the number of charge per unit volume V. Q stands for charge on each of the charge carriers, L for the length of the conductor. Now we are going to derive a formula. The total number of charge passing through the conductor is NV. Why is it NV? We already know N means number of charge per unit volume. So if I take N into V, that is the total number of charge passing through the conductor. Volume is the product of cross-sectional area into length. So our cross-section is A and our length is L. So volume is equal to A into L. Total charge passing through the conductor for a time t is equal to NALQ. As you can see, one charge carrier will have Q charge. If I'm having NAL charge carriers, if I need to find the total charge, I have to multiply the number of charge carriers by the amount of charge. So therefore, the total charge passing through is NALQ. The current is equal to total charge over time. We already found our charge as NALQ. Over time is T. I can rearrange it like this, NA L over T into Q. Length over time talks about the average velocity, which is our drift velocity. This expression is valid for both positive and negative charges. Summary: electric current is the rate of flow of charge. Conventional current is the flow of positive charge from positive to negative. In metals, current is carried by electrons which travel from negative to positive. The coulomb is the unit of charge and is an ampere second. Charge can be calculated using Q is equal to IT. For a current carrying conductor, total current is equal to MAVQ. So we have covered all these points. In the next video, you will learn about potential difference and power, which is the second subtopic of this unit. That's it for now. If you have any questions, leave it in the comment below. I'll get back to you as soon as possible. If this video helps you, give it a thumbs up and please consider subscribing to my channel. Thank you.